Seminar. Good morning. Sorry, good afternoon. For me, it's good morning here. Today we are happy to have Dr. Matt Hilton from University of Witwatersand and KwaZulu-Natal University. I'm not sure if I'm pronouncing those university names right as a speaker. Matt's research interest includes CMB cosmology, and he has been actively involved in ground-based facilities such as Atacama Cosmology Telescope and Science Observatory. Uh, Matt completed his PhD from Liverpool John Moores University, and then he moved to KwaZulu-Natal University, and then University of Nottingham for his postdoctoral research before joining his current role as a professor at Witwatersand University. So today, Matt is going to tell us about the cosmology and galaxy clusters from the recent analysis from the Atacama Cosmology Telescope. So thank you so much, Matt, for joining today, and over to you.
Hey, thanks for having me. Okay, yeah, so I'm going to talk about cosmology and clusters from ACT. So this is the Atacama Cosmology Telescope as it was. So this was an experiment in Chile, saw first light in 2007 and ran up to 2022. And you may have seen earlier this year, we've had a 6th data release. So this is probably the last data release because the telescope's been decommissioned. So I don't think we'll do another one. We'll probably move on to Simon's Observatory is the next big thing. So I'll say something very briefly about that at the end. But yeah, okay. So this is the outline of the talk. I'm going to talk a bit about the Atacama Cosmology Telescope itself and the collaboration a little bit. I'll briefly mention the DR6 results, what we've had so far. And then for most of the talk, I'll be talking about the galaxy clusters. So this is now out on the archive as of a few weeks ago. So we've got the ACT data release 6 cluster catalog and all the products associated with that. So this is about 10,000 clusters detected with the thermal Sunyaev-Zel'dovich effect. So I've got the, I'm sure I can see my pointer. So we've got the archive link there for you there. And there's also like all the products are out on the web page there. So these will be on Lambda eventually, but at the minute they're on a server at WITS until we, get everything accepted and all and things settle down. Okay, so this is the collaboration. So this is a picture from a few years ago. By the end of the project, so it's kind of winding down now. We have about 160 people working on this project, and it's led from Princeton by Suzanne Staggs, with all these different institutes shown at the bottom. So mostly based in the US, but also, strong participation from other places as well. So this is a 6-meter telescope, which gets you arcminute resolution at millimetre wavelengths. So this is about 5 times better than Planck. And the reason for that is obviously you can extract more information from the CMB. And also this makes it much better for finding clusters using the SZ effect, which we're going to talk about in a bit. So the telescope saw first light in 2007, and then there's been 3 generations of detector technology. So we had MBAC, and then up to 2010, and then 2013 we had ACT-Pol, which added the first polarization sensitive detectors. And then from 2016 onwards, we had Advanced ACT, so the final receiver, which was a massive jump in terms of sensitivity. And that's allowed us to map like most of the southern sky, good sensitivity at millimeter wavelengths and high resolution. Okay, so this is a video of the ACT site. So this was put together by Simon's Foundation. So this is when ACT was still there. So this is a nice site for a bunch of CMB experiments. You can see it looks a bit like the surface of Mars. So this is like 5,000 meters, something crazy. And it's one of the highest and driest sites in the world. So you get above the water vapor in the Earth's atmosphere. So this is the telescope itself. This is the 6-meter primary mirror, as it was. And then this is the receiver cabin at the bottom with the Advanced ACT receiver in there. So with the 3 different arrays. So Advanced ACT observes at a few different frequencies. So we've had 150, so 90, 150, 220. And then there's also 30 and 40 gigahertz data, which hasn't been released as yet. Okay, and this is just showing how nice the sky is if you're in Chile. So it's one of the best sites to be. The pole is a bit better, but Chile is easier to get to, and you can see a lot more of the sky from there. Okay. Okay, and so the ACT Data Release 6 took place earlier this year. So this is a little visualization of the data you can get in that. So all these maps and everything is available on Lambda, has been since about March. So we're just going to zoom in and show the resolution of the ACT maps compared to Planck in a second. So with ACT, you can resolve some of these galaxies on this color scale here. So gray is the CMB, blue stuff is going to be dusty. So this is showing the Planck resolution now. Blue stuff is going to be dusty, red stuff is going to be synchrotron kind of sources. Okay, we're just panning around the map. So clusters will look as dark spots on this thing. So we're just going to pan around and see some other different sources in here. I'm not sure how this video is going to be doing on the Zoom, but we'll see. So we've got some resolved AGNs on here. So Fornax A, we can see this resolved spiral galaxy. You can actually pick out the spiral arms in the dusty channel, so the 220 gigahertz. And then this is just going to pan across to the towards the galactic plane now. So it gets increasingly dusty. There's more blue stuff turning up. Keep going. But this just illustrates that, this is a cosmology experiment, but this data is also useful for a whole bunch of other stuff. So there are people looking at galactic science with these maps. So you get nice arcminute resolution, polarization, sensitive maps of the galactic plane. So yeah, so if you've seen the Orion Nebula in the optical, this is what it looks like at millimeter wavelengths. Okay, so so the primary CMB results have been out since about March. So there's 3 papers associated with that. So I'm only going to briefly mention them here. So you can find a description of the maps and the main DR6 data products in Ness et al. So everything is available on Lambda. And then we had 2 big cosmology results papers. So we have Louis et al., which presents the Lambda CDM analysis and the primary, primary CMB power spectrum analysis. So here we've got the comparison between ACT and Planck. So you can see we're picking up some more bumps and wiggles as you go to higher resolution. And particularly ACT has moved quite a lot beyond Planck in terms of the EE mode spectrum. So the Planck error bars are much larger than ACT at these kind of L ranges. So Louis et al. Presents the main sort of lambda CDM analysis. And then Calabresi et al. is a paper about all the different extended models. And so this is a nice summary plot from that. So this is sort of answering the question, if we modify lambda CDM with all these different options like primordial perturbations, fiddle about with recombination physics, change things like to do with like neutrinos and whatnot, etc. Can you change the value of H0 you get from the CMB and bring it up to the Hughes value, the one measured from the Cepheid locally? And the answer seems to be, at least of this analysis, no. So even like in this case, you're still not getting to this Hughes region, but things are, still overlapping with this, the Carnegie Chicago Hubble program measurement of H0. So yeah. We also had results on lensing as well. So these came out earlier. So this is CMB lensing measurements from last year by led by Matt Avishal and Frank Koo. So we've got the lensing measurement is the red data points, and the black line on here was actually a prediction from the Planck 2018 results. So this is not a fit to the data. This is all like a blind analysis, and yet this is going through the data points, showing that, things are pretty close to lambda CDM in this case. And then on the right, we've got the parameters plot. So sigma rate versus omega matter. So with the lensing alone, you get, not hugely tight constraints, but when you combine that with the BAO, so not going through the primary CMB, you get this red contours here. So the Planck CMB, primary CMB constraints is this one. And so the sort of take-home message from the ACT DR6 lensing was that so this lensing measurement, you're measuring at a higher redshift than the galaxy shear surveys are doing, but you get a sigma rate which is fully in line with what's been found from the primary CMB, unlike some of the galaxy-based measurements of this. Okay. Okay, so moving on to talk about galaxy clusters. so with ACT, we're doing this through the SZ effect, so I'll get onto that shortly. But just as a quick sort of recap about clusters and why we care about them. So they're the most massive gravitationally bound structures we find in the universe. They're full of these red and dead elliptical galaxies that are no longer forming stars. So if you're interested in star formation in galaxies, this is a good place to study what's happening to them. And in terms of the composition, they're about 80% dark matter, 15% in the form of hot gas, which comes out at, you can see, at X-ray wavelengths, and then 5% stars. So all these lovely golden colored things here, these are the elliptical galaxies in this Hubble image of this cluster. This is just 5% of the mass of the cluster. And, you know, this is just like the tip of the iceberg. So this is a nice X-ray view of the coma cluster. So this just shows the hot gas. So the gas in clusters gets heated to 10 to the 7, 10 to the 8 Kelvin. And yeah, sadly, I'm not sure how much more we're going to see from the Russian side of the E-Rosita collaboration. So this is 2020. This is the image of the coma cluster. So nice extended X-ray blob with the 10 to the 7, 10 to the 8 Kelvin gas is what we're seeing here. Okay. And so, yeah, clusters, you can look at them at all sorts of different wavelengths and learn all sorts of different things. So if you're interested in the galaxy formation, if you look at UV you can look at star formation, if you could look at the UV, or you can look at the, dust obscured star formation with radio and infrared wavelengths. So this is a little picture of a radio image of a cluster with Meerkat, which we did last year. So this was a high redshift cluster where you're seeing a lot of the sources in there are powered by star formation as well as being AGNs. And then at the radio, you can also study the magnetic fields as well. So I'll mention something about that a little bit towards the end. And then for the hot gas, you can see that X-rays as we saw in that E-Rosita image. You can also look at the hot gas through the Sunyaev-Zel'dovich effect as well, which turns up at millimetre wavelengths like what ACT observes. So what is the SZ effect? So this is the inverse Compton scattering of cosmic microwave background photons by the high energy electrons in the hot gas in clusters. So the cartoon view is over here. So this wobbly blue shape is supposed to be the cluster atmosphere, the 10 to the 7 Kelvin gas. And some fraction of CMB photons coming through the universe are lucky enough to pass through a cluster, and some fraction of those are lucky enough to encounter an electron on their way through. They exchange energy, and the photon gets scattered upwards in energy. Okay, so it goes to the bluer wavelengths or high frequencies. So what we can do with the SZ is use the CMB as a backlight to find all the massive structures in the universe. So the size of this SZ signal, this Compton scattering effect, just depends. It's a measure of the integrated thermal pressure along the line of sight, and that scales with the mass of the cluster. Okay. This thing at the bottom is just showing the spectral distortion. So if you look at the maps of the sky at different frequencies, you see a cold spot at low frequencies and a hot spot above 220 gigahertz. Okay. So yeah, so if you can measure this effect, you can use this to find all the massive clusters in the universe. That SZ signal, so that Comptonization parameter is scaling with the cluster mass. And that's really what you can use to use clusters for cosmology. So although this effect was predicted back in the 1970s, it's only in the last 20 years or so we've been using this to find clusters for cosmological surveys. So the first blind detections were done by the South Pole Telescope back in 2009. So this paper by Stanisevsky et al. Okay, so just briefly, how do we go about finding clusters in the SZ? So we're going to exploit that spectral distortion of the SZ effect, and also the fact that clusters are compact on the sky. So what we do is we use this to make what's called a multi-frequency matched filter, and all the high-res CMB experiments have used this. So Planck used a variation of this, SPT does, and we do also. So I've been a bit lazy, so this is actually an ACT DR5 map for these next couple of slides. So this shows a blow-up of part of the map at 98 gigahertz. The cloudy stuff is the CMB. The white blobs are mostly AGNs, which are, a pain if you're interested in the clusters. And then over here, we've got a cluster showing up as a dark spot. So this is 98 gigahertz. You can go to 150. And then you can apply your match filter, which uses the SZ spectral signal, and also the fact that clusters are compact on the sky. So you've got a sort of profile of what a typical cluster might look like to construct the match filter. And then your match filter map will look something like this. So now the clusters show up as bright spots. So this is a signal to noise map. So we've just highlighted a bunch of clusters here. And so this allows you to you can measure their SZ signal from this and all that kind of stuff. But to do anything useful, you need to go away and get redshift measurements and things like that. And so you have to go to optical telescopes. And so this is, I think, a legacy survey image of one of the clusters. So this is slightly updated from DR5 because I'm not sure this particular image was there, but this is a redshift 0.7 cluster. So you're looking for, red galaxies. You can measure the photometric redshift, or this one we have a spectroscopic redshift, but whatever. And then you can find where all the clusters are in the universe. Okay, as long as they're massive enough to be picked up by your survey. So this is the sort of compulsory history of the universe slide for cosmology talks. So we've all seen this a million times. So the CMB is over here. We're using that CMB as a backlight to see all the clusters through the SZ effect. So we're over here. And basically, the kind of cosmological experiment you want to do with clusters, or one of them, is to measure their growth over cosmic time. So gravity builds up bigger and bigger structures as we go towards the right here. So we've got, a few 10 billion years or whatever to build up, clusters to be, 10 to the 15 solar mass things we see at lower redshift. And the rate at which that changes, so the number of massive clusters we see as we look back through the universe, depends upon the properties of dark matter, dark energy, and everything else. Okay, so we can use this as a probe of cosmology, which is independent of everything what's going on in the CMB, for example. So to actually do this in practice, so for the theoretical part of this relies on n-body simulations. So this is just a video of one from Klaus Toller's group of a forming galaxy cluster in a dark matter only simulation. So the dark matter is the white blobby stuff here, and we've got matter streaming in along filaments to build up a massive cluster. We've got a little redshift clock at the bottom. And so the idea is to use these simulations to measure the halo mass function. Okay. And then the name of the game is going to be relating that halo mass function at different redshifts to the things that we can actually observe. Okay, so this is a bit more of a busier plot with this kind of thing on. So this is work by Sébastien Bocquet back in 2020. What this is doing is taking a bunch of n-body simulations. So they've got about 100 different variations of these things. So you've got the halo mass function, so the number of halos as a function of mass, so M200C being mass here. And this is colored by each of these different realizations, so different cosmological parameters, different dark energy parameters, and things like that. So you can see there's a spread in these things. One generic feature is obviously it takes time for gravity to build up bigger structures, so there's massive clusters seen at low redshift. You don't see those things by the time you get to redshift 2. And this plot on the right is kind of showing the same sort of thing again. So again, the cluster mass function at different redshifts. So the idea is, well, this is halo mass. So the trick is going to be relating halo mass to the observables and everything else. But the idea is you see the number of massive clusters change through cosmic time. And that's the thing we want to measure. Okay, so the sort of generic recipe for doing this kind of thing is firstly, you've got to find an observable quantity that is going to scale with the cluster mass. So in our case, we're going to use the SZ comptonization parameter. Okay, so that's going to that correlates with mass. You then want to search the sky for clusters and measure that for all of your clusters. You then need to quantify how complete your sample is as a function of your observable. And that might depend on your noise level, for example. So that varies with sky position and ACT. So we have to worry about that. You then want to calibrate the relationship between your observable quantity and your true cluster mass. So we measure SZ Compton Y, for example. The way we do the mass calibration is to do stacked weak lensing at the moment to find out how much of our, signal that we measure corresponds to actual mass. And then you go away and you compare the number of clusters you detect as a function of this observable and redshift with the predictions from the halo mass function. So in the theory side, what you're doing is starting from the halo mass function and trying to transform that into whatever observable you measure. So this is the usual forward modeling thing. Okay, so yeah, the state of the art in this for SZ clusters is still the South Pole telescopes. It's been a while since we've weighed in on this with ACT. So this is again work by Sébastien Bocquet in 2024. And really, these two plots are just illustrating the potential power of clusters. So this is SPT with about 1,000 SZ selected clusters. So you can bear that number in mind when I say what we've got in DR6. So this sort of, I don't know what color this is, reddish, orangish thing. This is the SPT cluster results and sigma 8 and omega matter. So you can see these are it's quite nicely constrained. So this is using 1,000 SZ clusters plus weak lensing calibration from Dark Energy Survey. There's a bunch of other cluster surveys on here. And then just to show how competitive this is with other probes, this is the same thing, but this is the ACT DR6 lensing result. So just the lensing alone, you can see with the clusters, independent of what's going on in the CMB, you can also nail down these parameters. But the crucial part of this is nailing down that mass observable relation. So calibrating your signal to your actual cluster mass. In this case, done through weak lensing. So there's potentially a lot of power in these things. Okay, so for ACT, it's a long time since we've done this. So our last cluster cosmology result is way back in 2013. So this is what we got then. This was simpler times, getting constraints from about 15 clusters. Since then, because of all the jumps in, the improvement in the detector technology, basically, and the improved receivers and things, and allowing us to survey massive areas of sky, the size of the cluster sample has gone up by a couple of orders of magnitude. So this is a little fun plot of how the number of clusters found by ACT evolved over time. So we start off with, less than 10. We're at 180 or so by 2018. By DR5, there's this huge jump to about 4,000. DR6, we've got about 10,000. Okay, so this is the recent thing out on the archive in the last couple of weeks. Also, this orange point is Matthias Klein's independent analysis of DR5. It's using our cluster finder code, which is public, but using more up-to-date optical and infrared data to get redshift for clusters, which wasn't available when we did DR5. Okay, but this is, shows you make your data public, you make your code public, people can actually go away and use it and get something out of that. Okay, so I'm just going to briefly spin through the differences between the DR6 and DR5 analyses. So the first difference is we've added another frequency for DR6. So the 220 gigahertz data is better, so we do make use of it. So there is no SZ signal at 220 gigahertz, but it does help a little bit with subtracting out the CMB a bit better. So we still use it. For DR5, we only add data up to 2018, so DR6 adds all the rest of the ACT data up to 2022. So we use all the data which is usable. That includes data from the daytimes, because we don't have the same restrictions on data quality that people looking at the CMB power spectrum do. We also have this new multipath filtering and source detection pipeline. So with the code, you give it one configuration file and it can do all these different steps. So one of the things we were trying to do was basically find the sources and the clusters and keep track of everything simultaneously. One of the reasons for doing that was so we could attempt to, for example, recover a cluster signal at places which might be affected by point sources. This was not terribly successful, but we gave it a go. But yeah, so we have these multi-step process. So firstly, finding the brightest sources, which we have to mask and infill those. Then the sources we subtract is everything above signal to noise 5 in each frequency. So we track where source subtractions happen in the map, so we can track which pixels are affected. Then we do 2 passes for the clusters. So the reason why we do these 2 passes is when we're constructing the match filter, we use the map itself to construct the noise part of the filter. And so if that's got clusters left in it, that will give you a slightly biased answer. So we find the clusters first, subtract them, and then we estimate everything in the final step. And so we keep everything with signal to noise greater than 4. Okay. In terms of the flagging, this is a bit more sophisticated. So again, we're tracking where we've subtracted sources. So we will include candidates which might be affected by sources, but there'll be a flag there so you can throw those out, which is generally a good idea. And then we've got some post-processing flags like regions which are affected by dust. So we get that from the Planck 353 gigahertz map. There's also like annoying extended objects which can mess things up. So things like nearby galaxies or planetary nebulae. Again, we flag those regions. and then also regions near bright stars. So these don't affect your SZ signal, so they're not going to give you artifacts that way. But what they do is make it hard to get the redshifts. So if you want to get a complete sample, you may want to neglect those areas. So that's there. And so if you want to play with the code and the data products, you'll actually be able to fiddle with, if you don't like how we flag things, you can do things differently pretty easily. In terms of the redshift, so this is also updated. So this paper for the DR6 cluster catalog is a collaboration between ACT, Dark Energy Survey, and HyperSuPrimeCam. And so from our colleagues on Dark Energy Survey, we've got the RedMapper and WASP Y6 catalogs. So WASP has just recently become public, but RedMapper isn't as yet. And we've also got the Camera S23B catalog from HSC, which is not public yet as well. Outside of those regions, we've got an awful lot of overlap with the DECALS survey. So the legacy surveys, so DECALS DR9 and 10 catalogs are very useful. So Matthias Klein has got a bunch of these based on this MCMF work. There's Mad Cows 2 came out last year. So there's a lot of high redshift clusters from there. And ERAS also came out last year. So this is eRosita. So we use a bunch of those through cross-matching, but we also do our own photo Zs and spec Zs for a lot of stuff from public data where we can. And yeah, one other big change in terms of how we report things is the mass calibration. So we're now reporting masses by default using something which is consistent with weak lensing measurements. So in previous papers, similar to Planck as well, our calibration was based on this X-ray based calibration from Arnaud, which turns out to give you masses about 30% less than what you get from weak lensing. So our default presentation is now swapped around that way. Just briefly on estimating the masses. So this is the equation which we use. So the thing that we measure is Y0 twiddle. This is our central Comptonization parameter at a fixed filter scale. And then the thing we want to infer from that is the mass. And so we've got a normalization. So this is the thing which has changed for the account for the weak lensing mass calibration. Then we've got a power law slope. This is almost linear because we're using central Comptonization. And then we've got a filter mismatch function, which accounts for the fact that different clusters have different sizes on the sky. So with some modeling, you can figure out what the effect of that is on the filtering. So the benefit of this approach, it's all described in this now ancient paper by Matthew Hasselfield, is that you basically can do everything on one single scale and model the rest of the stuff out of this, rather than having to run it cuts down the amount of computation you have to do basically to get completeness and things. And then we also have a relativistic correction. Okay. So in terms of the mass calibration, so there's the calibration we've chosen for DR6 is consistent with what's been found from follow-up observations of DR5. So this is a couple of papers from collaboration with kids, so the kilodegree survey. So the thing which people are measuring here, so MSZ over MWL, so this is SZ mass, if you assume the Arnaud X-ray based calibration over the weak lensing mass, which you can take as truth. People like to parameterize this as 1 minus B. So that's what this is. And so there's a bunch of different measurements here, but this is the kids one, which is somewhat higher precision, but more things are more or less consistent with these other weak lensing studies. And then we've done similar stuff in collaboration with HyperSuPrimeCam. So here they've plotted things the other way up. So we've got weak lensing mass over SZ mass, if you assume the Arnaud scaling relation. And this has now binned up in different redshift bins. So with HSC, because you've got more background galaxies, you can split this up and look at it at different redshifts. And at the moment, we don't see any evidence for evolution in the mass calibration with redshift. Okay. Right. So moving on to DR6 itself. So this shows where we've looked on the sky. So this black outline is the full footprint which has been searched. So if you want to look at the cluster candidate list, it's drawn from this area. This includes some pretty dusty areas of the sky, which was less fun to look into than we initially thought. But if you're interested in looking at that, all the information is there. And then we've got the various different optical surveys on here. This pink region is the Russian half of eRosita. So we have a roughly 50-50 split between the German and Russian halves. So everything which is not in the pink bit, that's in the German section. And yeah, this orange line is the footprint we've defined, which we're calling the ACT legacy footprint. So this allows you to define a complete sample of about 3,700 clusters if you've got a signal noise greater than 5.5, which is sort of suggested if you want to do some sort of cosmological analysis. And yeah, all this these products are available at this URL. Okay. And yeah, this is just showing where the actual clusters are. So the blue stuff is everything, so about 10,000 clusters with redshifts and mass estimates and everything. And then the 3,700-ish legacy sample is the orange ones. So this is a higher signal to noise subset. So it should be if you want a complete cluster sample, that should be the one to use. So using our machinery for estimating the masses and completeness, we can make these sort of mass completeness limit maps. So this is for signal to noise greater than 5. And this basically just reflects the different depths we had in ACT from all the different ACT surveys we've had. So you can see this bit on the equator is the deepest part with the lowest mass limit. And yeah, it's somewhat less deep in other parts. Okay, so this mass completeness relies on the modeling assumptions, right, and going in the scaling relation, so translating our noise to some sort of limit in SZ signal to some sort of limit in mass. Okay, but this shows how it varies on the sky. And then this is like the cumulative plot versions of those. So you could pick, say, if I want to find out how much area where the mass limit is better than 4 times 10 to the 14 solar masses, then it's of order 6,000 degrees or something. Like the full survey area is of order, the fully usable survey area is probably about 13,000-ish. Yeah. Okay. So we've also done a bunch of simulations to sort of validate all these things. So the way we've done this is we paint clusters into simulated maps. So we take the halo mass function, we assume a cosmology and some scaling relation parameters and a pressure profile for the clusters. And we use that to paint clusters into the maps at the different frequencies. And then we add noise to that following what's been seen in ACT DR6. We also add a little bit extra to sort of simulate what atmosphere does. And then we convolve everything with the appropriate beams. So we have a bunch of simulated maps, and then we run the cluster finder, the same setup as used for DR6, the real clusters on it. And then we check what we recover from those with the predictions from the model. So we do this for 30 different realizations. So this is the number of clusters, well, signal to noise 5, that we see as a function of redshift. So the colored lines are the different realizations, and then the black line is the median of those realizations, and the red is the average theory prediction. So that's for versus redshift, and this is versus signal to noise. So this little Q twiddle symbol is our signal to noise at this fixed filter scale. And so hopefully these things look quite good. So hopefully, fingers crossed, we ought to be able to move on to try and do some sort of cosmological analysis with these kinds of things fairly soon. And this shows the same kind of thing. This is just a residual, so the catalog minus a prediction. So the blue error bars here is what you get for one realization, so your Poisson error. And then this is the stacked 30 average of the 30 sims. So they're within that scatter. So the hope is that this should be good enough to go ahead and start doing some cosmological analysis shortly. Yeah, let's see on that one. So coming back to the real cluster sample, so this is what our mass and redshift distributions look like in this sample. So the key thing to take away from this is we've got an awful lot of clusters at high redshift. So more than 1,000 at redshift greater than 1, and more than 100 at redshift greater than 1.5. So the slight caveat with that is that a lot of those are photometric redshifts. So the orange line is a spectroscopic. There's only a couple of high redshift clusters known at almost redshift 2. So a lot of these will be things which are in MADCAM. So here what we're doing is effectively with the ACT catalog, you can use that to tell you which of the MADCAM's 2 clusters are the most massive ones at high redshift. It is one way to look at it. But there's a slight caveat with the fact that these are photo Zs, and in an ideal world, you'd want to go and confirm these, because when you get above redshift 1.5, things are quite sketchy with the photo Zs generally. As a general rule. Okay. And this is the kind of traditional summary plot of mass versus redshift of all the different, of a bunch of different surveys. So this is comparing ACT with various SPT catalogs and also ERAS. So these have all got the same mass calibration to within about 10%, so they're roughly comparable. So basically, ACT, we've got a lot more clusters than the SPT ones at the moment because we've gone wide and they have gone deep. So we're plotting our stuff behind theirs. The deepest SZ observations are by SPT in this small area, this SPT deep survey. And then ERAS is very good at detecting low mass clusters at low redshift, but is struggling to see the higher redshift things. So these things are complementary. Okay. One of the things we asked with our overlap with ERAS is, are we missing any massive clusters? So you would think with ERAS and ERAS is X-ray selected, ACT is SZ, we're both detecting clusters based on the ICM. So if you see any clusters in ERAS, which we don't, that would be like an indication that we've got some problem with source contamination that we need to account for. And so this is something we know does happen. So if we have seen some cases where you've got a VCG, so a brightest central galaxy in a cluster, hosts a radio source, and if that radio source is bright at 90 gigahertz, then it can potentially wipe out your SZ signal. So one of the things we were trying to do with the source subtraction business was to see if we could recover some SZ signal. Turns out, based on this plot, that it's not terribly successful. So for ERAS, we selected a sample of things we think ACT should have seen. So that's things with M500 greater than 5 times 10 to the 40 solar masses, redshift greater than 0.2. And it turns out we end up missing about 8% of those, or at least they're recovered at ACT signal to noise less than 5. So this plot is showing this thing. So what we've done is we've done forced photometry. So at the ERAS cluster positions in the ACT maps, we run our machinery to estimate the recovered mass at that location. And then we compare it to the mass in the ERAS catalog. So this line here is the one-to-one line. So things are generally recovered around that. You can see there's a huge amount of scatter with somewhat of a tail towards lower masses. And then these orange points are ones which we know are definitely affected by 90 gigahertz sources. So we know the bottom line from this sort of preliminary analysis, so again, this could be done in more detail later on, is that about 2 to 3% of the clusters are definitely sort of missing in ACT compared to ERAS for these, even for these massive clusters. For the ones in between, it may rely on, because we're using forced photometry to do this, it may rely on the positional accuracy. The positions could be affected by a sort of like low-level AGN contamination that we don't detect. So, you know, basically the 2 to 3% is definitely affected, and there's possibly a tail up to, you know, maybe 6-7% above that. There are a few cases we could throw out where this is the reverse problem, where there's clusters which have got X-ray AGN. So these have got yeah, the ERAS masses in those cases are not supposed to be trusted. Yeah, so it's going to be a while before we can do actual cluster cosmology with DR6. But just for the release paper, we've at least asked the question, do we see any clusters that would break lambda CDM? So this is your mass versus redshift plot for the ACT DR6 sample. This pink region is defined by these old school Mortensen et al. Sort of lambda CDM exclusions curves. And from this, we see a couple of clusters which are pretty extreme. One of these is El Gordo. So this was found very early on in ACT. It's a crazy merging system. So two roughly equal mass lumps of 10 to the 15 solar masses colliding at redshift 0.87. So this is the image with the X-ray overlaid on the infrared. So yeah, and then this is El Gordo 0.87. The other one, which we're particularly highlighting here, is at redshift 1.23. And so what I think is quite interesting about both these cases is they're both cluster mergers. So for El Gordo, the SZ mass we infer in ACT DR6 is about 30% higher than the weak lensing mass measured with HST. For this one, this is a cluster at redshift 1.23 where we don't have as much information, but which we followed up with Meerkat. So we detect a radio halo in this. And radio halos are seen in colliding galaxy clusters. So they're probably sort of transient, like a couple of 100 million years, they probably hang around for. But basically what's happened is you've smashed two clusters together, and through the turbulent reacceleration of electrons in intracluster medium, you can get them to shine through synchrotron radiation at radio wavelengths. And so the fact that we see this in this cluster tells us it's probably, again, a merging system. But we don't have any other information on this one at the moment. So we're trying to get some follow-up observations, so spectroscopy and such like, to really, see exactly what's going on with this one. But this is kind of suggestive that some of these guys, even if they are sort of like pushing these limits, are actually boosted by the fact that they're mergers. Okay, so I'm almost done. So just the final bit. So I'm just going to very briefly mention Simon's Observatory. So ACT is finished, decommissioned in 2022, and the telescope itself is hanging out at some museum kind of place near San Pedro. So this is the ACT site, what has been transformed in recent years by the Simons Observatory. So this is a new project. So the small aperture telescopes over here in their ground screens, some of which have been taking data since 2024, I think, the first one. These are looking for the B mode signatures from gravitational waves in the early universe. And then we have a new large aperture telescope over here. So this saw first light back in March this year. It's a 6-meter telescope, so exactly the same resolution as ACT, different design with a larger focal plane, because the way you win now with the sensitivity of the individual detectors is to be able to build a bigger focal plane and pack in more detectors. And so this is now taking data. So we're on the phase of getting some initial observations, and maybe, I suppose, in the next 12 to 18 months, we might start to see some results come from Simon's Observatory. So on the clusters front there, you're expecting of order 30,000 clusters with signal to noise greater than 5. So yeah, and if you go down to signal to noise 4, which is what we do for the ACT, it's about 70,000, I think you expect, depending on the simulation you're using. But yeah, we're going to expect a huge increase in the number of clusters. So again, the name of the game is going to be calibrating these things well enough to extract all the cosmological information. Okay, so I'm going to stop there. So this is a quick summary. So firstly, ACT DR6 is out. So you can get the papers about the power spectrum analysis and all the maps, and the likelihood is been on Lambda since March. The cluster catalog is now out, so that's available with the link at the bottom. That'll be on Lambda once we get the paper accepted, so that we don't have to change things if we want to fiddle with stuff. Source catalogs are going to come out soon, so that's at quite an advanced stage, but it's not out yet. We've talked about the SZ effect. So we've gone from having 10 SZ selected clusters with ACT to about 10,000 over the lifetime of the project. Cosmology is going to take a little time to come from the cluster sample. But the sort of like first order thing we've done is, at least we can say we've searched this huge volume. We haven't found any cluster more extreme than El Gordo, even though we found El Gordo in the first couple of years of the project. And yeah, so everything for this work is public, so you can get the cluster search products. They're probably going to get slightly updated in the next week or so to match the final DR6 thing, because I'm writing this tutorial on how to reproduce everything. And so, things have changed a little bit with an upgrade of one of the libraries which is used. But yeah, you can get the source code. You can also get the documentation. Like I say, there'll be instructions for reproducing all this stuff if you're interested. So I'm going to stop there. Thanks.
Thank you, Matt, for a nice presentation. So, all right, it's time for questions. Please feel free to raise your hand and take the mic. Joby?
Hi, can you hear me?
Yes, you can.
Oh,
Yeah.
okay. So, possibly a naive question, but does this SC effect allow us to break the degeneracy between galaxy intrinsic alignments and weak lensing?
No. No, I don't see how you'd be able to do that.
Is it like an independent estimate of the mass distribution?
So with the resolution of these SZ experiments, so that like SPT or ACT, you'd, apart from stuff which is very nearby, you don't resolve the clusters terribly well. So we basically get one number out of that pretty much. So SPT likes to use signal to noise as their mass proxy. We're using this like central Comptonization parameter. So yeah, so that gets you an estimate of mass, and we're going through the weak lensing to calibrate that relationship. But yeah, we don't have anything to say on intrinsic alignments through this. For that, you have to look at the galaxies themselves.
So when you say you have good resolution only for the nearby, only to very close redshifts, very nearby objects, what is nearby? What do you mean by nearby? How, like, till approximately what redshift is nearby?
So yeah, so things which are going to be like if you're interested in doing cluster physics on the nearby clusters, rather than go through this like matched filter business, you're better off making these component separated maps. So we have these Y maps in Coulton et al. And so if you want to look at low redshift, so I'd say like redshift 0.1 or redshift 0.2, those you can like look at those clusters and actually try and look for features in them, even with just the ACT data. But like the ones which are high redshift, so our median redshift is 0.6, you can't really do anything like measure a profile, for example.
Thank you.
Okay. So, any other question? Okay, I had a question. So, you mentioned about the dust and said that, okay, so you haven't looked at close to the galactic plane. So maybe an add question. So I was just wondering, do we really need to worry much about dust? I mean, galactic dust, because you're looking at very small scales and dust is a large scale thing, galactic dust. Also, the spectra is going to be different. So is there a proper quantification of the bias galactic dust make on these kind of measurements?
So if the dust is large and fluffy, then that's true. It's not really a problem for the SZ if it's like on larger scales. You do sometimes get these clumpy bits though as well, which if you're unlucky with those, they can contaminate things. The main reason why you want to avoid the dusty regions is more to do with the follow-up. So it's probably quite likely. So part of the reason why we extended our mask, it goes quite close to the galactic plane. So we do have candidates there. So it's quite likely that there are clusters there. But you know, when you go to the optical infrared data, you get swamped with if you're in a high stellar density region, it's quite hard to get redshifts and such like. So it's not impossible, but it's harder. So it's more to do with the optical and infrared rather than the yeah.
Yeah, it makes sense. Yeah. Thank you. Any other questions?
So how is the ACT noise compared to the Planck noise or WMAP noise? Uh, is the scale smaller or is it lower?
I can't remember off the top of my head. There's some comparisons in the Ness et al. Paper I mentioned at the start. So he like Sigurd has plotted these things as a function of scale in that paper. Yeah. So this Ness et al. Paper. So I think we're certainly like, we're obviously beating Planck on small scales. But on the largest scales, then Planck is still winning. Yeah, but on the very largest scales. So we because like things like atmosphere and stuff like that is an issue for ACT. So we don't get to the smaller scales. You can see on these power spectra we have a cut of about L of 500-ish or something, 600. Yeah.
Okay.
But if you want the full gory details per band, I think there are plots in Sigurd's paper, like the noise as a function of scale for the different bands.
Okay.
Okay, any other questions? Okay, so I don't see any other raise hand. So if not, let's thank Matt once again. Thank you so much for joining and giving a nice presentation. Okay, so let's wind up here. Bye.
Thanks. Bye-bye.